Welcome to the Deep Dive. Today we're plunging headfirst into the, well, incredibly rapid and multifaceted evolution of AI. It really feels like every single week brings some new breakthrough or a new legal challenge, maybe a seismic shift in how the big players are strategizing.
It's moving fast, really fast.
Exactly. So our mission, as always, is to try and cut through that noise and unpack the really crucial recent developments. We're talking everything from legal battles and big corporate power plays all the way through to cutting-edge research, how it's shaking up society, and the foundational tech making it all actually tick. Think of this as your essential shortcut, really, to being truly well-informed on AI's latest stuff. We'll throw in some surprising facts and practical implications you might be able to apply.
Yeah, and we've pulled from a pretty diverse stack of sources today, everything from specific court rulings, internal corporate memos, detailed research papers, even broad economic surveys, so a real mix.
It's definitely going to be a fascinating journey.
Indeed. And what we're really aiming to do here is distill what truly matters from these, well, seemingly disparate pieces of information. It's not just about reporting the headlines, right? It's about providing that critical context, understanding the deeper implications, maybe seeing the bigger picture of where AI is heading.
Right.
So the core question we'll kind of keep coming back to throughout this deep dive is, what do these developments, from a landmark legal ruling on data use all the way to a groundbreaking new low-precision model, what do they tell us about the trajectory and, maybe more importantly, the challenges of AI, especially from a technical, critical, and pragmatic viewpoint?
Okay, let's get to it then. Let's unpack this with a truly foundational piece of news. This one has massive implications. A major legal ruling on AI training and copyrighted materials. So a United States District Court recently weighed in on whether training large language models, LLMs, on copyrighted books constitutes fair use. This was a really significant case brought by a number of authors against Anthropic, one of the big AI model developers.
Yeah, this ruling is incredibly significant. It really is, because it directly addresses one of the, let's call them, major risks to AI progress.
Okay, what are those risks?
Well, generally, people identify three big ones that could truly slow down innovation. First, you've got regulatory capture, especially if regulations end up stifling open source development, maybe in the name of AI safety, but really just centralizing control.
Right, like big players locking things down.
Exactly. Second, losing access to cutting-edge semiconductor chips. Think, for instance, a major geopolitical event, like a war involving Taiwan. That could cripple the supply chain overnight.
A scary thought.
Definitely. And third, regulations that severely impede access to data for training these AI systems, making it too expensive or legally too risky to actually acquire the data you need.
Okay, so this ruling hits that third one.
Precisely. This ruling from Judge Elsup directly mitigates that critical data access risk. It essentially says that training LLMs on legitimately acquired copyrighted books is fair use, which is, well, it's a potential game changer because it clears a huge legal hurdle for AI development, at least for now, in this specific court.
That is a huge shift.
Yeah.
And the judge's reasoning was quite memorable, wasn't it? He drew that analogy.
Yeah, the school children analogy. He basically said the author's lawsuit is, and I'm quoting loosely here, no different than if they complained that training school children to write well would result in an explosion of competing works.
Huh, interesting. It's like saying learning is learning. Whether it's a human or an AI, it's about building capability, not just copying. Puts AI in the role of a student, almost.
Exactly. And this kind of sensible approach to data access is just vital for the industry. I mean, while the mass media often focuses on, the sheer scale of data centers or how many parameters a model has.
Right, the big shiny numbers.
Yeah. But if you talk to the companies actually training these huge foundation models day to day, a massive chunk of their challenges revolve around data preparation. It's not glamorous, but it's crucial.
So it's not just dumping data in.
Oh, absolutely not. It's about what we call data-centric AI practices. This means a really meticulous, structured approach. You're identifying high-quality data, and books are super important here, very structured, rich content. Then there's meticulous data cleaning. The ruling even mentioned Anthropic removing headers, footers, page numbers from scanned books.
Right.
Then you're doing constant error analysis to figure out, okay, what data are we missing? What do we need more of? And sometimes you're even inventing new ways to generate high-quality synthetic data to fill those gaps. So this ruling, it genuinely reduces a major barrier to just getting the work done.
So it's a clear win for data access then. But I'm curious, Were there any parts of this ruling that were not a win for Anthropic? Any
Hmm.
areas where the judge maybe put his foot down?
That's a really good question. And yes, it's crucial to understand the specifics. It wasn't just a blanket do whatever you want with data.
Right.
The ruling did clarify that Anthropic converting physical books to digital format for training is also fair use, which, makes practical sense. Digitization is necessary. However, a crucial loss for Anthropic was the judge's stance on pirated materials.
Ah,
The ruling was very clear. Training on data you legitimately acquired, fine. Using pirated materials like, say, texts downloaded from pirate websites, that is not fair use, full stop.
got it.
And another point, permanently building a sort of general purpose library of texts, just storing them indefinitely without permission, maybe for future undetermined uses, also not considered fair use.
That's a critical distinction. So if an LLM provider, maybe, has been sourcing data from, let's say, less than legitimate channels, they're now on notice.
Exactly. They'll likely need to revisit their data sets and practices if they include pirated works. This means more compliance work, more due diligence. It could lead to significant data reevaluation across the industry.
So what are the immediate and maybe longer-term implications here, assuming this ruling holds up against appeals? Because these things often get appealed, right?
Oh, absolutely. Landmark rulings like this almost always face appeals. It could take years, potentially go to higher courts, maybe even trigger legislative action down the line. But if it stands, the overall impact is pretty positive for AI progress.
How so?
Well, perhaps the biggest benefit is just reducing ambiguity around AI training and copyright. It makes the roadmap for compliance much clearer for developers. The message is, you can train on legitimately acquired data, even copyrighted books, to build transformative models. Converting print for this is okay, just make sure your acquisition is responsible.
Okay, that clarifies things for the tech side. But this definitely raises that important question about the human element again. I mean, while the ruling might be great for AI innovation, it clearly impacts content creators, writers especially. How do we critically look at balancing those benefits with the potential disruption for creative professionals?
Absolutely. And the source we looked at acknowledges a very real sympathy for writers worried about their livelihoods. It's a critical, ongoing societal challenge, isn't it? How do we balance the huge benefits of, let's say, free access to more data for AI training, which fuels innovation, creates potentially amazing tools, with the very legitimate need to fairly compensate those individuals or groups who are, well, significantly negatively affected by AI's rise?
Yeah, it's tough. If an AI can write a novel in minutes,
Yeah.
what happens to human authors?
Exactly. There's no simple fix. It's a complex ethical, economic dilemma. Society will have to grapple with it, maybe through new economic models, different licensing frameworks, perhaps even discussions around things like universal basic income. It's a big, thorny issue.
And that tension between innovation and human impact seems like a perfect lead into our next topic, how the big tech players are scrambling, making massive strategic moves to secure their own AI future.
Precisely. It connects directly.
So here's where it gets really interesting on the corporate front. Just look at this massive move from Meta. They're not just collaborating with Scale AI, the data labeling startup. They're essentially recruiting its leadership and pouring billions into it. What's the story here? Why is this deal such a big deal?
Well, it's fascinating because this deal doesn't just inject capital into Scale AI. It fundamentally reshapes the whole competitive landscape for data labeling services, which, remember, is a foundational piece for building AI.
Right, the data preparation we just talked about.
Exactly. So the deal effectively doubled Scale AI's valuation. It went from about $13.8 billion last year to a staggering $28.1 billion after this agreement. Meta acquired 49% of the startup,
Almost half.
almost half, but crucially, in non-voting shares.
Ah, why non-voting?
That's the clever part. It's likely designed to give Meta the benefits of a close partnership, influence, access to the tech and talent, without triggering the intense government scrutiny an outright acquisition might bring. The FTC has been looking closely at Meta's past deals like Instagram and WhatsApp, so they're probably being cautious about full mergers right now.
That makes sense. A way to get the benefits without the regulatory headache.
Yeah.
So what exactly does this deal give Meta, and what does it mean for Scale AI besides the cash?
It's definitely multifaceted. It's a clear play for both talent and data. First, Meta explicitly recruited Scale AI's founder and CEO, Alexander Wang, plus key members of his team directly into Meta.
The young billionaire founder, right?
Yeah, the one who became the world's youngest self-made billionaire, founding Scale AI as a teenager back in 2016. He's now set to oversee a new Meta research lab specifically focused on developing superintelligence. So that infusion of high-profile talent. Huge strategic motivation for Meta, especially given some of their recent perceived struggles in AI.
And the data aspect.
Right. Second, the deal grants Meta priority access to scale AI's extensive large-scale data operations. And again, high-quality labeled data is the absolute lifeblood of advanced AI models. It's what helps them learn patterns, understand context, perform complex tasks. So Meta gets top talent and preferential access to the fuel.
Okay, and what's the immediate fallout for the rest of the industry? I mean, I can't imagine Google or OpenAI are exactly thrilled about their competitor getting this cozy with a key supplier.
Oh, the competitive consequences were immediate and pretty stark. Since news of Meta's investment broke, some of Scale AI's other major customers, including direct competitors like Google and OpenAI, announced they'd be looking for new providers for their data labeling.
Wow.
It really highlights the cutthroat nature of AI competition right now. Alliances can shift fast, and partnerships can suddenly become competitive disadvantages.
So for Meta, this was really about grabbing that talent. You mentioned struggles.
Yeah, from Meta's perspective, the talent acquisition seems paramount. The source material points out Meta's AI efforts have faced some headwinds. Their Llama 4 model got a bit of a cool reception. There were reports, anonymous employees telling Fortune that Meta's AI lab felt like it was dying a slow death earlier this year. Plus, their AI research chief, Joel Pineau, stepped down after 8 years.
So this deal is like a shot in the arm.
Exactly. It's Meta clearly signaling they are on a mission to add firepower to their AI divisions. They'd already been talking about acquiring other firms like Safe Superintelligence, that's Ilya Sutskever's new company, formerly from OpenAI and Perplexity AI. This Scale AI deal is an aggressive, very calculated play to secure top-tier expertise and really accelerate their AI ambitions.
So what does this signal for the broader AI community, and specifically for talent? Are we going to see AI engineer salaries just go through the roof even more?
It's a clear, unambiguous signal, isn't it? It shows the immense value being placed on top-tier AI talent and access to high-quality training data in this race for AI dominance. Meta's willingness to spend such an immense sum for talent. Yeah, it absolutely could boost engineer salaries across the industry. It might make it harder for competitors with less deep pockets, or maybe even open source projects, to attract that same caliber of expertise.
That's a potential downside for competition.
It could be. But on the other hand, Meta has historically made some really valuable contributions to the open weights model community, like Llama 4. We can speculate, maybe hope, that this new super talented team, focused now on superintelligence within Meta, could significantly advance the capabilities of open models too.
That would be interesting.
Yeah, making them even more competitive with the closed source giants. That could be a massive benefit for the broader AI ecosystem, fostering more innovation, more accessibility.
So from securing the foundational data and talent via these big corporate moves, let's shift now to see how that data and talent are actually being leveraged to build, well, truly advanced practical AI applications.
Good transition.
This next piece delves right into that practical application side. It showcases a really fascinating, potentially game-changing development in scientific research, an AI agent called Biomni. It's designed for broad biological research. And this isn't just some niche tool. It's described as an agent capable of performing tasks across numerous biological specialties. Think genomics, zoology, the whole gamut.
Right.
And it's a big collaboration. Stanford, Princeton, University of Washington, Arc Institute, Gentech. Plus, what's really exciting is they intend to release it open source.
Yeah.
So its capabilities could become widely available.
Yeah, this is a really powerful demonstration of how AI agents are moving beyond being narrow, specialized tools. They're becoming broadly capable research assistants. It feels like a significant leap forward in making AI genuinely useful across diverse scientific fields.
So how does it actually work? What's the engineering behind something so broad?
Well, let's dive into the technicals because that's where the real insight is.
Yep.
The authors basically assembled this vast collection of tools, software packages, databases, all relevant to biological research. Okay. The core mechanism is pretty neat. You give it a prompt, maybe a complex research question. It then uses a copy of Claude 4 Sonnet, a powerful LLM, to figure out which specific resources it needs, which tools, which software, which databases. Then it prompts the model again to build a detailed step-by-step plan to actually produce the response or solve the problem.
So it's using the LLM to orchestrate the research process itself.
Exactly. It's not just retrieving information, it's actively planning and executing a research strategy.
Okay, but research rarely goes perfectly according to plan, right? How does it handle that iterative process, maybe when things go wrong or it needs to adjust?
Right, good point. It follows something called the CODACT framework. What that means is, given a prompt maybe to follow the plan or maybe to act on the results of some code it just ran, Biomni can do several things. It can ask the user for clarification if needed. It can write Python code. It can execute that code in its environment. And then it returns the results.
Okay, so it can code and run things.
Yes. And it keeps doing this cycle, follow the plan, maybe write code, execute it, reason about the results iteratively until it's ready to give a final comprehensive answer. But critically, there's a built-in quality control step that makes it much more reliable.
Yeah, how does that work?
At each intermediate output step, a different copy of Claude 4 Sonnet acts as a judge.
That's check.
Yeah. This judge looks at the output and assesses, did the agent follow the proper procedure? Or did it kind of confabulate, hallucinate or make stuff up?
Right.
If the judge thinks the agent fell short, it tells the agent, nope, repeat that step until it gets it right. If the output looks good, execution just continues normally. It's a very practical way to try and ensure reliability and stop errors from snowballing.
That is clever. A built-in fact checker almost. And how did they even build up the initial knowledge base for something covering all of biology? That sounds like a monumental task.
It was definitely rigorous. It speaks to those data-centric AI principles again. They started by prompting Claude 3.5 Sonnet, which was the state of the art, when they began to extract relevant tasks, tools, and databases from a huge set of 2,500 recent scientific papers.
Wow.
And to make sure they got breadth, they specifically chose 100 papers from each of 25 different biological specialties.
Okay, very systematic.
Very. Then human experts manually filtered that massive initial list down. They ended up with about 150 core tools and nearly 60 key databases. Then they added around 100 popular biological software packages on top of that. It's this meticulous data collection and curation that gives Biomni its incredible breadth and depth. It essentially has access to a vast library and the tools to use it.
So the big question,
Mhm.
how well does this broad-spectrum biology agent actually perform? I mean, does it live up to the hype when you test it?
Well, the results they reported are quite compelling. They definitely show a significant jump in capability compared to just using an LLM on its own.
Okay, give me some numbers.
All right. On the lab bench subset of humanity's last exam, that's a tough biomedical benchmark, Biomni got 17.3% accuracy. Claude 4 Sonnet alone, only 6%. Even Claude 4 Sonnet, with access to our research tool, got just 12.2%.
So a noticeable improvement from the agent framework.
A substantial improvement, yeah. It shows the value of having the agent orchestrate the tools and the reasoning process.
Those are impressive benchmark scores. But what about, real-world tasks? Could a scientist actually use this for something complex in the lab?
That's where it gets even more tangible and, frankly, exciting. They ran several practical case studies, for instance, diagnosing a patient based on their full genome sequence. Biomni achieved roughly 85% accuracy. Claude 4 Sonnet alone, just 5%.
Whoa, that's a massive difference. 5% versus 85.
Huge difference. It really highlights the agent's ability to navigate and correctly apply complex genomic data. Another cool example, producing protocols for cloning DNA sequences.
Okay, like lab instructions.
Exactly. Actual step-by-step lab protocols. Experts rated Biomni's protocols around 4.5 out of 5 across 10 different tests. That put it on par with protocols generated by human experts. Notably better than human trainees, and miles ahead of what Claude 4 Sonnet could produce alone.
On par with human experts. That's amazing.
But here's the real clincher, the proof of practical application. A DNA synthesis lab actually took one of the protocols Biomni generated and successfully produced this specified DNA sequence in the real world.
No way. So it went from digital instructions to a physical biological result.
Exactly. It's not just theoretical output. It's a validated physical outcome that demonstrates genuine utility in a lab setting.
That is incredible. So how does Biomni compare to other AI agents people have built for biology? Is it really that different?
It clearly distinguishes itself. There have been other biology agents, sure, but they were typically much narrower. Think Cell Voyager for single-cell RNA data, or CRISPR-GPT for designing gene editing experiments, or Spatial Agent for analyzing cell interactions.
Right, very specific tasks.
Exactly. Biomni's power is its domain-spanning knowledge, its ability to pull together information and tools across these different areas, something those specialized agents just couldn't do. It's like upgrading from a set of specialized wrenches to a highly versatile, intelligent multi-tool for biological research.
This really shows the potential for AI to augment human expertise in a profound way, doesn't it? Not just automating one task, but helping scientists connect dots they might miss because their own expertise is so specialized.
Indeed. Biomni demonstrates that these agents can pull together resources from sometimes disparate areas of knowledge to reach novel conclusions. That's incredible. That's the beauty of the design. It's adaptable. You can swap in newer, more capable LLMs as they come out. You can continuously update its library of tools and databases to keep pace with scientific advances, even extend its knowledge into new biological areas. That ensures its long-term utility. It's designed to be a dynamic, evolving research partner.
Wow. Okay, so from that highly specific, advanced scientific application, let's pivot now to a much broader and maybe even more immediately impactful societal question. How AI is being perceived to affect the global workforce, jobs. This is a very real, very human concern that touches pretty much everyone.
Absolutely, a critical topic.
Okay, so let's unpack one of the most talked about implications of AI, its impact on jobs. We've actually got some incredibly candid statements from CEOs of major U.S. corporations. These offer direct links into how top leaders are thinking about AI and their own workforces.
Yeah, and this is a crucial real-world concern for individuals, industries, entire economies. But while these executives are, well, quite vocal about AI's potential to reduce headcounts in their specific companies, it's really essential to look at the broader data, the more complex trends beyond just these individual corporate statements. We need a critical, nuanced view here.
Okay, so who are we hearing from and what exactly are they saying? Lay out the specifics.
All right, well, starting with Amazon. CEO Andy Jassy, in a memo to employees, and by the way, full disclosure, I should mention Andrew Ng, a prominent AI figure, is on Amazon's board. Jassy's memo stated, and I'm quoting here, "We will need fewer people doing some of the jobs that are being done today and more people doing other types of jobs. In the next few years, we expect that this will reduce our total corporate workforce."
Wow. Reduce the total workforce. Given Amazon employs, what, 1.5 million people? That's potentially huge.
Significant, yeah. Even a small percentage is a lot of people. Then you have Brian Moynihan, CEO of Bank of America. He's publicly said he expects widespread use of AI in banking would lead to a smaller workforce industry-wide, suggesting efficiency gains could mean fewer human tellers, fewer back-office roles across the board.
Okay, banking too. Who else?
IBM CEO Arvind Krishna, he noted that AI agents have already replaced hundreds of workers in their HR department. Now, he did qualify that by saying overall employment at IBM actually went up in other areas, maybe driven by AI growth in software or consulting, but still direct replacement in HR. Then there's Shopify. CEO Tobias Lutke apparently issued an instruction back in April. Before employees request new hires, they first have to explain why AI isn't sufficient to meet their goals.
Whoa. So AI is the default assumption for getting work done now.
That's the implication. AI first, human second, almost. And finally, Laura Alber, CEO of Williams-Sonoma, told investors their plan is to focus on using AI to offset headcount growth this year, meaning basically avoid adding new employees even if the business grows by using AI instead.
Okay, so that's a pretty clear pattern from these major players.
Yeah.
Caution, efficiency focus, potential reductions or slowing of hiring due to AI. And you mentioned a World Economic Forum survey backing this up.
Yeah, that survey suggested 40% of employers globally expect to downsize due to AI. So it seems like a widespread sentiment among business leaders, at least. It paints a pretty stark picture.
It does. But you said we need a more nuanced view. What's the counter-argument or the other side of the story based on broader data?
Right. It's crucial to balance those CEO statements and employer surveys with broader economic studies. Several recent analyses actually suggest AI is likely to increase or at least have little net effect on the total number of jobs in the economy.
Really? Increased jobs?
Well, for example, researchers at the European Central Bank looked at nearly a decade of data and found that employment in occupations affected by AI actually rose, and with little impact on wages.
Huh. Why would that be?
It's complex, possibly because AI made existing jobs more productive, allowing companies to expand, or maybe it created new tasks within those existing roles that needed humans. Another study from the U.S. government found employment grew in 9 out of 11 occupations considered potentially subject to automation.
Okay.
And PricewaterhouseCoopers, PwC, they analyzed almost a billion job ads internationally, They found job availability grew 38% in roles considered more exposed to AI. Now, that growth was slower than in less exposed roles, but it was still significant growth, not decline. It suggests more of a recomposition of work, a shift in skills needed, rather than just jobs disappearing.
So despite what some CEOs are saying about their own companies, the bigger economic picture maybe tells a different story. Is this just like past technological shifts, like the Industrial Revolution, where old jobs go but new ones are created?
That's exactly the historical perspective. Estimates suggest something like 60% of U.S. jobs that existed in 2018 simply did not exist back in 1940.
Wow.
Think about it. Web developers, social media managers, cybersecurity analysts, entire industries didn't exist then. Technology has consistently, over the long run, created more jobs than it destroys by creating new needs, new services, new possibilities, new industries.
So we should expect new AI-related jobs.
We are highly likely to see an explosion of new roles. Machine learning engineers, obviously, but also AI application engineers, prompt engineers, AI data specialists, AI ethicists, maybe even entirely new job categories we can't even conceive of yet.
Yeah.
That historical context is really critical.
Okay, so putting this all together, what does it mean for individuals, from someone listening right now trying to navigate this landscape? How should they prepare for this future where AI is just increasingly part of every job?
Yeah, that really brings it down to personal agency, doesn't it? In the face of this huge technological change. Look, there will likely be short-term disruption, especially for knowledge workers, maybe creative people, roles we once thought were safe from automation. That seems unavoidable.
Right.
But the long-term outlook points towards that explosion of new roles requiring different skills, a different way of working. Probably the most practical advice comes from adapting that message Andy Jassy gave his Amazon employees. It's really a universal call to action for everyone.
What was the core message?
Basically, be curious about AI, educate yourself, attend workshops, take trainings, use and experiment with AI whenever you can, participate in your team's brainstorms, figure out how to invent more quickly and expansively, get more done with scrappier teams.
So lean in. Don't run away.
Exactly. The critical takeaway, the pragmatic advice for listeners is clear. Those who actively embrace AI, learn about it, figure out how to integrate it into their workflows, they will be significantly more productive. They will likely outperform those who don't. It's about adaptation and becoming AI literate. It's a skill multiplier.
Okay, that makes sense. Adapt or risk being left behind. So from these broad societal implications, let's dive deep now into a specific, really nitty-gritty technical innovation. One that promises to make AI models much more accessible and efficient, directly impacting how this technology can actually be deployed and used more widely.
Perfect. Let's get technical.
All right, let's unpack some truly cutting-edge technical details. This next piece is all about making large language models incredibly efficient. We're focusing on a development called BitNet B1.58. Now, just for context, the general idea here is model quantization, right? Reducing the bits per parameter, say, from 16 bits down to 8 bits to shrink the model size, make it faster.
Exactly. Less memory, faster computations.
But this research we're looking at from Microsoft, University Chinese Academy of Sciences, Tsinghua University, they take this to an absolute extreme. They've built a competitive LLM where the weights, the parameters, are limited to just 3 possible values, -1, 0, or +1.
Yeah.
That just sounds almost impossibly restrictive. How can that even work?
It's fascinating, isn't it, how this seemingly tiny change in precision going from, floating point numbers with lots of decimal places down to just 3 integers forces a complete rethinking of the entire LLM training process, down to the fundamental hyperparameters.
So why do it? What's the core technical insight?
Well, the key insight is realizing just how critical linear layers are within a transformer's architecture. They make up huge chunks of both the attention mechanism and the fully connected layers, which means they account for the vast majority of the computations when the model is running.
Okay, so optimizing them gives you the biggest bang for your buck.
Yeah, exactly. Now, the trade-off with traditional 1-bit weights where you only allow -1 and +1 is that while multiplication becomes incredibly fast, multiplying by -1 just flips the sign, times +1 does nothing, the overall performance, the accuracy of the model often suffers quite a bit.
Right, too restrictive maybe.
Potentially. So the innovation, the really sensible decision with BitNet B1.58 was allowing the value 0, adding 0 back in. This lets the network effectively zero out, or ignore certain connections, which gives it more flexibility. It retains the low memory footprint and the fast training inference benefits you get from near binary weights, but it dramatically improves performance compared to pure 1-bit.
And that's where the 1.58 bits comes from.
Precisely. It's just the math.
Hmm.
Log base 2 of 3 possible values, negative 1, 0, plus 1, equals roughly 1.58. It's just a precise way to quantify the information capacity of each weight.
Okay, I got the why, but the how. How do you actually train a model with such extreme low precision without completely wrecking its performance? It sounds incredibly tricky to balance that.
Yeah, this raises the really important question about practical implementation. And you're right, it's definitely not just flicking a switch from high precision to low precision. It requires a very carefully designed, quite nuanced training regimen.
Okay, walk us through it.
All right, so first, the model itself, it was a 2 billion parameter BitNet B1.58. Architecture kind of similar to Meta's Llama. It was pre-trained on a huge data set, 4 trillion tokens, mix of web data and synthetic math problems.
For a trillion tokens. Okay.
Then, to really boost its reasoning, they fine-tuned it on chat data, instruction-following data, even synthetic instruction-following data. And finally, they used DPO, direct preference optimization. That's a pretty cutting-edge technique to align the model's outputs better with what humans actually prefer, make it sound more natural, more helpful.
Okay, so lots of data, lots of tuning. But what about handling the precision itself during the actual training steps? Constantly switching between bit depths must be complex.
That's where the core technical trick lies. During training, the authors used a clever approach. They used the quantized version of the model, the naive 1, 0 plus 1 version, for the forward passes. That's when the model is making predictions.
Right.
But for the backward passes, that's where the model learns, calculates gradients, updates its weights. They use the non-quantized full precision version of the weights.
Okay, so they keep a high precision copy.
Exactly. So before each forward pass, they take the full precision weights and quantize them, snap them to -1, 0, or +1 for the linear layers. The outputs of the layers are also quantized, but to 8 bits. Then the forward pass runs fast, but when it's time for backpropagation to calculate the updates, those updates are applied to the non-quantized high-precision weights. Then, those updated high-precision weights are copied and quantized again for the next forward pass.
Okay, that's clever. You get the speed benefit of low-precision forward passes, but maintain the accuracy needed for learning in the backward pass.
Precisely. It's a neat way to get the best of both worlds during training.
And what about other parts of the model? And I heard something about two-phase hyperparameter schedules.
Yeah.
That sounds deep in the weeds, but I'm intrigued. What's that about?
Right. So for practical reasons, things like the attention mechanism, layer normalization, other operations, they were run in 8-bit precision, kind of a middle ground. But critically, the gradients and the loss function itself, which guide the whole learning process, those were stored in 16 bits to maintain accuracy during the weight updates. You don't want noise there.
Makes sense. Now, these two-phase schedules.
Yes, this is where the real ingenuity comes in, and it's absolutely critical for making this extreme quantization work effectively. Think about teaching someone a complex skill. You might start with big, broad instructions, then move to finer, more subtle corrections later on.
Okay.
That's essentially what they did with the learning rate, the step size the model takes during learning. They started with an initial high learning rate. Why? Because with these 1.58-bit weights, a tiny change to the underlying high-precision weight might not actually be enough to flip its quantized value from, say, 0 to +1 after rounding.
The updates might get lost in quantization.
Exactly. So a high learning rate ensures the updates are large enough to actually have an effect on the quantized weights, to get the model learning quickly in the right general direction. But then this initial high rate phase was followed by a sharp drop in the learning rate mid-training.
Why is that drop?
This second phase, with a much lower learning rate, allows the model to make finer adjustments to really refine its weights precisely, especially as it starts training on higher quality data without wildly overshooting the optimal values.
Okay. High then low for learning rate. What else?
They did something similar, a two-phase approach for weight decay. That's a technique to prevent overfitting, basically penalizing large weights. In the early phase of training where the data might be noisier and the learning rate is high, they applied strong weight decay. This stops the model getting too attached to potentially bad data early on, helps it generalize better.
Right.
But then in the second phase, with higher quality data and that lower learning rate, they actually disabled weight decay entirely.
Turned it off.
It's a sensible choice. At that stage, you want the weights to fully adapt to the good quality data without being artificially held back or shrunk by the decay mechanism. You let the model fine-tune without interference. These kinds of careful, structured adjustments to basic hyperparameters, that's what allows BitNet B1.58 to achieve such good performance despite the extreme low precision. It shows a really deep, practical understanding of the training dynamics.
Okay, that's fascinating how much thought goes into just tuning the training itself. So what kind of real-world performance gains did all these incredibly nuanced changes actually lead to? How did BitNet B1.58 actually stack up against other, maybe more conventional models in speed, memory, and crucially, accuracy?
Right. The proof is in the pudding,
Hmm.
and the results they reported are really compelling. They demonstrate very concrete, tangible advantages in speed and memory while staying remarkably competitive on actual performance. They tested it across 16 popular benchmarks covering language understanding, math, coding, the usual suspects. And BitNet B1.58 consistently came out faster and used significantly less memory than its competitors. These included models like Alibaba's Qwen 2.5 1.5B, Google's Gemma 3.1B, Meta's Llama 3.21B, and others in that sort of size class.
Okay, give us some numbers. Let's grasp the magnitude here. How much faster? How much less memory?
Certainly. So running on a typical laptop, which is a key use case for efficient models, BitNet B1.58 generated text at an average of 34.5 tokens per second.
Okay.
Compare that to Qwen 2.5 1.5B, a strong competitor, which managed only 15.4 tokens per second on the same hardware.
Wow, more than double the speed.
More than double. And the memory difference is equally, if not more, striking. BitNet required just zero point 0.4 gigabytes of RAM.
Zero point 0.4 gigs, that's tiny.
Tiny. Whereas Qwen 2.5 1.5B needed 2.6 gigabytes. That's a massive reduction, something like 6 times less memory. It makes it vastly more feasible to run on devices with limited resources, personal laptops, maybe even phones, or embedded systems out at the edge.
Incredible efficiency gains. But what about accuracy? Did they sacrifice performance to get that speed and size?
That's the key question, right? And remarkably, no, not really. BitNet achieved an average accuracy of 54.19% across their 16 benchmarks. Now, that was just slightly behind Qwen 2.5 1.5B, which scored 55.23%, so a tiny dip in accuracy.
Barely noticeable.
Pretty much. But importantly, BitNet still outperformed all the other competitors they tested against, including even a 4-bit quantized version of that same Qwen model, which only got 52.15%.
So it's faster, way smaller, and still beats most competitors on accuracy, only slightly behind the very top one.
That's the takeaway. It's a truly impressive balance.
So the real breakthrough here isn't just about making models efficient. It's about unlocking powerful AI capabilities for potentially everyone, everywhere on devices they already own.
Absolutely. I think the core message from this work is that achieving high performance with these extremely low precision LLMs isn't straightforward. You can't just apply the standard playbook for full precision models. It demands a really deep understanding, a fundamental rethinking of the entire training process, right down to those seemingly small hyperparameter choices. This research provides a concrete, practical guide for how to get good performance out of these super efficient models. And that, ultimately, makes powerful AI far more accessible, far more deployable across a much wider range of applications and hardware. It really does feel like, well, more than a bit of progress in making AI more efficient and usable.
Ha! Nice one. What a deep dive today.
Yeah.
Seriously, we've covered so much ground exploring these practical, sometimes groundbreaking changes happening in AI right now. We went from the absolute fundamentals like the legal framework around data and copyright.
The fair use ruling.
Right. Then through those huge strategic corporate moves, acquiring talent and data.
The meta and scale AI deal.
Yeah. To the incredible capabilities of new AI agents like Biomni in science.
Augmenting researchers.
Then tackling the very real human impact on the workforce.
The CEO statements versus the broader data.
Exactly. And finally, diving deep into these intricate technical innovations like BitNet B1.58, making AI models incredibly efficient.
Yeah, it's been quite a journey through the AI landscape, and I think the common thread weaving through all of this is just the relentless pace of innovation. And alongside that, the critical need for adaptability, both in the technology itself, constantly evolving, and in how we as individuals, as companies, as a society engage with it.
Absolutely.
The story of AI isn't just about the big, flashy breakthroughs you read in the headlines. It's so much about the intricate, technical, pragmatic details that actually make those breakthroughs possible, and understanding the broader implications they create for, well, pretty much every aspect of our lives.
Well said. So as you, our listener, reflect on this deep dive, here's maybe a final provocative thought for you to mull over. Given everything we've discussed, the recent legal ruling potentially clarifying fair use for data, these immense corporate investments pouring into data and top AI talent, and the emergence of these hyper-efficient, low-precision models that are so much easier to deploy. What new, truly disruptive business models might emerge now? Models that leverage this newly clarified landscape for data access combined with this much more deployable AI.
Interesting question.
I mean, consider how the combined effect of that legal clarity and this technical efficiency could unlock applications or collaborations that were maybe unthinkable even a year ago. How might that fundamentally change traditional industries we know today, like content creation or education or customer service? Something to think about.